Hi everybody, it's Professor Mitchell. We are finishing up chapter 4 today on number theory. And today we're going to be looking at section 4.3, greatest common divisor and least common multiple. In this section, we'll look at the greatest common divisor and least common multiple of two or more whole numbers by using a variety of methods, applications of GCD and LCM to word problems and their solutions, and the Euclidean algorithm for finding the greatest common divisor. So as an example of an application problem for greatest common divisor, two bands are to be combined to march in a parade. A 24-member band will march behind a 30-member band. The combined bands must have the same number of columns. Each column must be the same size. What is the greatest number of columns in which they can march? So the bands could each march in two columns and we would have the same number of columns, but this does not satisfy the condition of having the greatest number of columns. The number of columns must divide both 24 and 30. So if we look at numbers that divide both 24 and 30, we get 1, 2, 3, and 6. The greatest of these numbers is 6. The first band would have 6 columns with 4 members in each column, and the second band would have 6 columns with 5 members in each column. So the greatest common divisor, GCD, or greatest common factor, GCF, of two whole numbers, A and B, which are not both 0, is the greatest whole number that divides both A and B. Using colored rods, you can find the GCD of two numbers. For example, to find the GCD of 6 and 8 using the 6 rod and the 8 rod, you would find the longest rod such that we can use multiples of that rod to build both the 6 rod and the 8 rod. And when you see the picture, that might make more sense. You can use 2 rods to build both the 6 and 8 rods. So if you line 3 2 rods up next to the 6 rod, they're the same length. And if you line 4 2 rods next to the 8 rod, they're the same length. And furthermore, 2 is the biggest number that'll work for, because if you use 3 rods, you can build the 6 rod but not the 8 rod. If you use 4 rods, you can build the 8 rod but not the 6 rod. The 5 rod doesn't work for either, and the 6 rods cannot be used to build the 8 rod. Therefore, the greatest common divisor of 6 and 8 is 2. Another method is the intersection of sets method. List all members of the set of whole number divisors of the two numbers, then find the set of all common divisors, and finally pick the greatest element in that set. So to find the GCD of 20 and 32, let's denote the sets of divisors of 20 and 32 by D sub 20 and D sub 32. The divisors of 20 are 1, 2, 4, 5, 10, and 20. The divisors of 32 are 1, 2, 4, 8, 16, and 32. And you can see that the intersection of those sets is 1, 2, and 4. And the greatest element in that set is 4. Therefore, the GCD of 20 and 32 is 4. This might be my favorite method for finding GCD. It works even with great big numbers. To find the GCD of two or more non-zero whole numbers, first find the prime factorizations of the given numbers, and then identify each common prime factor of the given numbers. The GCD is the product of the common factors, each raised to the lowest power of that prime that occurs in any of the prime factorizations. And when we find numbers that have no common factors other than 1, those numbers are called relatively prime. For example, 4 and 9 are relatively prime. Here's an example. First let's find the GCD of 108 and 72. So the prime factorization of 108 is 2 to the second times 3 to the third, and the prime factorization of 72 is 2 to the third times 3 to the second. So the prime factors of our GCD are going to be 2 and 3 because both of the numbers have those prime factors. And now we're going to take the smallest exponent from each prime factor. So when we look at these, I see that the smallest power that 2 is raised to is the second power, and the smallest power that 3 is raised to is the second power. Therefore, the GCD of 108 and 72 is 2 to the second times 3 to the second, which is 36. All right, now this one, you would not use prime factorizations. We've never talked about a prime factorization for 0. I don't think that makes any sense. When one of the numbers is 0, your GCD is automatically going to be the other number. And that's because 13 divides 0 and 13 divides 13. Obviously, no bigger number divides 13. Therefore, the GCD of 0 and 13 is 13. All right, continuing this example, let's find the GCD of x and y. If x is 2 to the third times 7 to the second times 11 times 13, and y is 2 times 7 to the third times 13 times 17. So first, the prime factors that those two numbers have in common are 2, 7, and 13. The smallest power that 2 is ever raised to is first power. The smallest power that 7 is raised to is second power. And the smallest power that 13 is raised to, it's a tie, is first power. So that gives us 2 times 7 to the second times 13, which happens to be 1,274. All right, this next example, letter D, is very similar, except it has 3 numbers, but it's still the same idea. So this might be a good time to pause the video and try this one. We want to find the GCD of x, y, and z. If x is 2 to the third times 7 to the second times 11 times 13, y is 2 times 7 to the third times 13 times 17. So that's the same x and y from letter C. And z is 2 to the second times 7. So this time, the prime factors that those 3 numbers have in common are 2 and 7. The smallest power that 2 is ever raised to is the first power, and the smallest power that 7 is ever raised to is the first power. So the GCD of these 3 numbers is just 2 times 7, which is 14. And finally, find the GCD of x and y. If x is 5 to the 4th times 13 to the 10th, and y is 3 to the 10th times 11 to the 20th. So this time, those 2 numbers have no prime factors in common. And when your 2 numbers have no prime factors in common, that means the GCD is 1. All right, that brings us to the Euclidean algorithm, which I also really enjoy. If a and b are any whole numbers, with b not equal to 0 and a greater than or equal to b, then the GCD of a and b is equal to the GCD of r and b, where r is the remainder when a is divided by b. Finding the GCD of 2 numbers by repeatedly using the theorem above until the remainder is 0 is called the Euclidean algorithm. And this is what's called a flow chart that explains the Euclidean algorithm. So you start with your 2 positive numbers, a and b, divide the larger number by the smaller number. If the remainder is 0, then you're finished. The last divisor is the GCD. However, if the remainder is not 0, then you divide the last divisor by the remainder and then check again to see if the remainder is 0. And you repeat that process until the remainder is 0. So now we're going to use the Euclidean algorithm to find the GCD of 10,764 and 2,300. So first we divide 10,764 by 2,300, and we get that the remainder is 1,564. Since the remainder is not zero, we're going to repeat that, and this time we're going to find the GCD of 2,300 and 1,564. So we divide 2,300 by 1,564. The remainder is 736. So now we'll do it again. Divide 736 into 1,564. We get the remainder is 92. And so now we'll do it one more time. Dividing 736 by 92, we get the remainder is 0. That means the last divisor, which was 92, is the greatest common divisor. All right, here's an example of finding the GCD of 3 numbers. Any common divisor of 3 numbers is also a common divisor of any 2 of them. The GCD of 3 numbers cannot be greater than the GCD of any 2 of the numbers. So let's take 6,341 and 6,339. Now here, I think they're using a theorem that they didn't talk about, which says that a shortcut to find the GCD is to look at the difference of the 2 numbers and replace the larger number with the difference of the 2 numbers, and that really helps speed things along. Notice that this is the same thing that would happen if we just divided 6,341 by 6,339. The remainder would be 2. And then clearly the GCD of 2 and 6,339 is 1, because 6,339 is an odd number. It's not going to have any prime factor of 2. So the GCD has to be 1. Since the GCD of all 3 of those numbers cannot be greater than 1, it must equal 1. Now let me just say that if you were doing this with 3 numbers where the GCD of 2 of the numbers came out to be bigger than 1, you would then have to see, for example, let's say it came out to be 4. You would need to check and see, is 4 a divisor of the number that you left out? Okay, and if it isn't, then that means the GCD is smaller than that. All right, the GCD of any 2 consecutive whole numbers using the theorem that I just mentioned. So if you take the GCD of n and n plus 1, replace the n plus 1 with the difference of n plus 1 and n, and that's 1. So it's going to be the same as the GCD of 1 and n, which is, of course, going to be 1, no matter what n is. So the GCD of any 2 consecutive whole numbers is 1. All right, that brings us to least common multiple. And here's an example. This happens to be one of my favorite examples for least common multiple. Hot dogs are usually sold 10 to a package, while hot dog buns are usually sold 8 to a package. Why is that? It just doesn't make any sense. What is the least number of packages of each you must buy so that there is an equal number of hot dogs and buns? That's an example of using least common multiple. So the number of hot dogs would have to be a multiple of 10, while the number of buns has to be a multiple of 8. The number of hot dogs matches the number of buns whenever 10 and 8 have a multiple in common. And this occurs at 40, 80, 120, etc. So the least of those multiples is 40. which means if you want an equal number of hot dogs and hot dog buns, you need 40 hot dogs and 40 hot dog buns, which means you need 4 packages of hot dogs and 5 packages of buns. So here's the definition of least common multiple. The least common multiple, or LCM, of two non-zero whole numbers, A and B, is the least non-zero whole number that is simultaneously a multiple of A and a multiple of B. So for example, the least common multiple of 3 and 4 using the number line method, just count by 3s and count by 4s until you reach the same point. And the first time you reach that same point, that's going to be the least common multiple. So you see the first time that I ever reach the same point is at 12. The arrows do not coincide until the point 12 on the number line, therefore 12 is the LCM of 3 and 4. Using a 3-rod and a 4-rod, build trains of 3 rods and 4 rods until they're the same length. So this is kind of similar to the number line method, right? The LCM is the common length of the train. So you see with 3 4 rods and 4 3 rods, you get 2 trains that are the same length, and that length is 12. You can also use the intersection of sets method. So you would list all members of the set of positive multiples of the 2 integers, then find the set of all common multiples, and finally pick the least element in that set. To find the LCM of 8 and 12, denote the sets of positive multiples of 8 and 12 by m sub 8 and m sub 12. So here are the multiples of 8, here are the multiples of 12. Some of the numbers they have in common are 24, 48, 72, and the least of those is 24. Therefore, the LCM of 8 and 12 is 24. You can also use a prime factorization method. It's a little different than for finding GCD. To find the LCM of 2 non-zero whole numbers, first find the prime factorization of each number, then take each of the primes that are factors of either of the given numbers. So this time we're not just taking factors that they have in common. We're taking all the factors that occurred in either number. So GCD, it's more like the intersection of the prime factors. This is the union of the prime factors. The LCM is the product of these primes, each raised to the greatest power of the prime that occurs in either of the prime factorizations. So remember when we did it with GCD, we were using the smallest power. So for our first example, we'll find the LCM of 2,520 and 10,530. The prime factorization of 2,520 is 2 to the third times 3 to the second times 5 times 7. And by the way, I didn't do this in my head, right? I would use probably a factor tree to get that prime factorization. So please, 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 as you're listening to this, whenever I just come right out and say something, you know, feel free to pause the video and check it, all right? It's a good excuse to review your factor trees. And the prime factorization of 10,530 is 2 times 3 to the fourth times 5 times 13. So the union of all the prime factors that occur in those two numbers would be 2, 3, 5, 7, and 13. And the largest power on each of those prime factors would be, well, the largest power of each of those prime factors would be 2 to the third, 3 to the fourth, 5, 7, and 13. And the product of those powers is 294,840. All right, this is kind of a neat theorem that shows the relationship between the GCD and the LCM. for any two natural numbers A and B, the GCD of A and B times the LCM of A and B comes out to be A times B. So where this really comes in handy is when you know either the GCD or the LCM, or you know how to easily find it, then you can use this equation to figure out the other one without having to do a lot of work. So in this example, we're going to find the LCM of 731 and 952. So the way I'm going to do that is I'm going to use the Euclidean algorithm to find the GCD of 731 and 952. And you should try this one. All right, I'm just coming right out and saying that if you use the Euclidean algorithm, this is what you're going to get. So using the theorem that we were just talking about, since the GCD times the LCM is equal to the product of the two numbers, that gives us 17 times the LCM is equal to 731 times 952. So if we divide both sides of that equation by 17, we get that the LCM of those two numbers is 731 times 952 divided by 17, which is 40,936. That's going to do it for section 4.3, and that's also going to do it for chapter 4. So we'll see you next time.